So we're going to go through enthalpy changes and delta H reaction, exothermic and endothermic, and show you some really cool reactions that we've done. And enthalpy is another word for energy, and you use enthalpy instead of energy in a lot of situations in A-levels. So first of all, this is my hand, okay, in my lab, and I'm going to set my hand on fire. So there we go. You can see the hand is on fire, and you don't see I've got a really big smile on my face while I'm doing this. Okay, and that's an exothermic reaction. So energy is being given out to the surroundings. Okay, so the round of the surroundings, which is the air or the solution, the water and everything like that, gets hot because the chemical energy is coming out of the system and going into the surroundings and warming them up. So let's look at that in terms of a classic diagram that you would normally see. Now at GCSE, you see this as energy and progress of the reaction, and then we put the reactants, we put the products. The products have less energy than the reactants. That's a really important thing because the energy difference is given out to the surroundings. So we put the reaction we're going to do on there, and this reaction was CH4, which was burning to make CO2 and H2O. Now, at that point, okay, you can see the energy is going down. Therefore, we got an arrow there, single-headed arrow. So single-headed arrow going down. Okay, not a double-headed arrow, single-headed arrow pointing downwards. And that's your delta H. Then, from this point, this shows our activation energy, and hopefully you should remember this from GCSE. Okay, and you go to an intermediate then. We'll talk about that in further videos. Now, this is your activation energy. Okay, the energy taken to break all the bonds. Okay, now, and that is labelled E little a. Now, from this point, the definition is in the corner there. So the minimum amount of energy required for a reaction to occur in the green over there, and you do need to remember it. So this is your activation energy here. Now, from this point, I've now changed it to enthalpy, and it's changed to a negative. That's just showing you it's negative. Now, when you're labeling it in the exam, please don't put a negative on there. Okay, I'm just showing you this is a negative change. So it's a negative change. Now, because that's a negative change, okay, that's happening here, that means all of that energy from here to here, if you think of that as zero, and that is your product, all of this energy from here to here is going out into the surroundings. So we're saying that the chemical system has lost that much energy, and so we call it a negative value. Okay, now from that point, let's make it and show you the breaking of the bonds, sorry. So the breaking of the bonds is the activation enthalpy, or activation energy, sorry. Okay, there's where you're breaking the bonds, and this is how much energy it takes to break the bonds. And if you want to go through how calculations, go through the calculating delta H through bond breaking and bond making. But this is your breaking the bonds, and then going down the other side is your making of the bonds. So the energy is given out when you make, and the energy is taken in. So on an exothermic reaction, what we actually say is the energy taken in to break the bonds is less than the energy given out when the bonds are made. Okay, and that is how we do it. Now, that's written over the right. If you want to write over on the right, if you want to do your notes. Okay, and the example of exothermic reactions are respiration, combustion, and neutralization. Now, let's have a look at endothermic. And if you can remember from GCSE, why don't you try and draw endothermic before I do it? So stop the video and try and draw it. So here's an endothermic reaction: barium hydroxide, hydrated barium hydroxide with ammonium chloride, sorry, and that goes to this barium chloride, hydrated barium chloride, ammonia and water. And we did this in the lab. So there's my hands again, and this is the two solids mixed together, and we've put a little bit of water underneath because it's going to get so cold that the water is going to freeze and stick the beaker onto the piece of wood. So all I need to do now is put it together. So I'm going to take, I think in this one it's ammonium chloride which I'm adding. It doesn't matter which order you put it in, and you just add it in there, and then you give it a little bit of a stir. And so all I'm going to do is give it a little bit of a stir, okay, and once it stirs and mixes, it starts to go really, really cold. And it starts, you'll see, it starts to clump up. It takes, oh, there it is. Can you see the clumps? See, it's starting to clump up. Now, if that's the case, that is starting to get cold. Starting to get very cold. So this should start to come down. You can probably just about see it from where you are. You can see it's coming down. Can you see this? Blue, and there we go. We zoomed in on it, and you can see it's going down. Okay, so this is an endothermic reaction, the surroundings are getting colder, okay? And you can also see the ammonia is turning this indicator paper, okay, the colour to a kind of like a bleach or a purple. Eventually it would go white if it got left long enough. But anyway, and there you can see it is frozen to the beaker, okay? And that's just because the ice, it's that cold that the ice has frozen. And there you go. Now, let's talk about endothermic reactions. The energy has been taken in from the surroundings, okay? And the temperature of the surroundings go down. So in this case, the surroundings is going to be the glass around it and the air around it and all of that, okay? So the chemical is taking in the energy, so the energy must go up for the chemical, okay? But the energy of the surroundings has gone down, which means that that has frozen. So let's have a look at this again. Okay, this time the reactants have gained energy, taken that from the surroundings. Remember, the surroundings get colder because they've taken that energy away from the surroundings and put it into the products. So if that's the case, the arrow must go up with a full head on the top, okay, and that is your delta H again. We then put our intermediate again at the top of the hump, essentially, okay, and then we do our activation energy. Notice a much larger activation energy here than before. And we've got enthalpy here as well, but if you are energy, nobody cares, okay? So there you have it. Now, I'm just going to put the plus on again. The plus is on again just to show you, look, it's a positive energy change. The surroundings get colder, but there's a positive energy change for the chemicals in the system. Remember, if you're doing it in the exam, don't write the plus on there, just write delta H. You've got the breaking bonds here, which is your activation energy, and your making of your bonds is here. So we've broken all the bonds, and then we're making all the bonds here. So in this case, the energy taken in to break the bonds is far greater than the energy given out when the bonds are made. Okay, and again, that is on the right there for you to use and write down in your notes. That is exothermic and endothermic reactions. Units of enthalpy for the next one is kilojoules per mole, okay, kilojoules per mole. So in GCSE, it was kJ/mole. Now it's kJ mole minus 1, okay? And so the delta H of this is minus 890 kilojoules per mole. So you can see there are multiple reactants here. And this is a really important point. That's 2 and that's 1. If it says kilojoules per mole, it's always referring to the lowest number of moles, or the ones that's the lowest. So here, we've got 1 mole of the methane, so it's referring to minus 890 kilojoules per mole of methane. Okay? Now, if it's 2 moles of methane, you just times the number by 2. So in that case, if we had 2 moles of methane, you would give out 1,780 kilojoules of energy to the surroundings. Now we're going to do a last bit of this video is the question, or the very common question, and it's quite hard. Okay? So hydrogen fluoride gas can be made by hydrogen and fluoride gas. Hydrogen fluoride gas can be made from hydrogen and fluorine gas added together. So here we have our 2 gases added together. And we can see it's an endothermic reaction there, plus 44. Okay. Complete the enthalpy change diagram, label the enthalpy change, label the activation energy, okay. Include the formula of the reactant and products, calculate the activation energy of the reverse reaction, very important the reverse, and calculate the enthalpy change at RTP when 20 moles of HF is decomposed. Okay, so calculate the enthalpy change there. So let's put that up there and let's go straight into it. So here it is, we've drawn it for you. Here it is, you've got your EA there, you've got your enthalpy change, you've labelled it, you've got your products, you've got reactants, you've got enthalpy, and you've labelled both your axes. So you've done all of the first bit. Okay, so that's all good. Now, let's make it so it's smaller. So we've got some space to put some other stuff in, and let's start looking at these ones under here. Calculate the activation energy of the reverse reaction. Now this is something people don't always get. So we want the reverse. It's the reverse. So we want it to go from here to here. Now it's important to note, and this is for the next question we're coming up as well, that if you're going in that direction, it'll be positive, and if you're going in this direction, this will turn to minus 544. Minus 544. But that's for a different question, but very, very important. Right, I want to do the activation energy of the reverse reaction. So let's look at this and find out where the activation energy of the reverse is. Well, here, if we did the reverse, we're going this way. This means this would be the reactant and this would be the product. That means you follow this line and then it goes up But the first hump is always the activation energy. So the activation energy starts here and goes to here. Okay, so it starts here, goes to here. Now, if that is the case, okay, if I know activation energy and I know the delta H, I know that the difference between the activation energy and delta H must be this number here. So the activation energy is up here, 586, and the delta H is here. So all I need to do is 586 minus 544, which is 42. So basically the activation energy is 42, or 42 kilojoules per mole. Okay. Next one. Calculate the enthalpy change at RTP when 20 moles of HF is decomposed. Okay, so you've got 20 moles of HF. So 20 moles of HF is decomposed and it's going in that direction because it has to be decomposed that direction. Now, 544 kilojoules per mole is given out to the surroundings going this way. So the value of minus 544 going that way. But every time you get minus 544 going that way, it's done for 2 moles of HF. So 2 moles of HF going that way. I've got 20. So therefore what I do is I take the 20 moles and divide it by 2, which means I'll have 10 lots of HF will be 20 moles of HF. So 10 times this reaction will be 20 moles of HF decomposed. So then going in that direction is going to be a minus enthalpy change, not a positive, it's a minus because we're going in the opposite direction, so it'll be minus 544. So minus 544 times 10, okay, which is minus 5440, okay. So we did the 20 divided by 2 first of all, 20 moles divided by 2, because for every reaction we're using up 2 moles. And then we do 10, which is 20 divided by 2, times the minus 544, which gives us a final enthalpy change of minus 5440 kilojoules per mole for the reaction when there's 20 moles of HF being decomposed. And that is the end of our enthalpy changes video. I hope you enjoyed it and I hope you learnt something. Have a great day.